Hey guys, so welcome to this video on the quantum mechanical model. So we have focused on talking about how light acts like a wave and how light acts like particles, and we are now talking about, right now in class, we're talking about Planck's constant. We're going to associate that with Bohr's model. Remember that I did tell you that Bohr's model only worked with hydrogen, so then here comes Schrodinger with a new solution, and his solution, or his model for the atom, was the quantum mechanical model. So we are going to look at that. We're going to look at it a little bit more detail. There are these concepts known as quantum numbers, and you're going to probably feel a bit overwhelmed, I'm sure, because this whole chapter has been a bit overwhelming. But we are going to talk about this in class, and it's really not as terrible once you start seeing patterns, especially when we start labeling the periodic table. So don't worry. Again, we will take this step by step. All right, so after this video, hopefully you'll be able to understand the de Broglie wave equation and how it illustrates the wave nature of the electron. So again, we're associating electrons, a particle, with waves. Understand how the Heisenberg uncertainty principle and Schrodinger's wave equation led to the idea of atomic orbitals. Know the four quantum numbers and how they are related to the arrangement of electrons in an atom, and finally describe the interrelationship between principal energy level, sublevel, orbital, and electron spin, and how they are related to the number of electrons of an atom. So again, a lot of probably foreign things that I'm saying right now, but we're going to take it step by step. So the de Broglie wave equation. And so first of all, this guy has an amazing name, and I really don't think I'm saying it right, but it's okay because his name is, I just think de Broglie. So anyway, Louis de Broglie derived an equation to show how particles can act like a wave. So yes, we know this. We're talking about Planck's constant, photoelectric effect. All of these ideas all tie in the fact that light can act like a stream of particles and a wave. And so here comes Louis de Broglie, and then he derives a new equation basically saying that wavelength equals Planck's constant divided by mass times velocity. So this accounts for the speed and the mass. And basically now he's focusing on electrons, because electrons, while small and almost have no mass, they still have a mass. So not like a photon where there's like absolutely no mass. Electrons actually have a mass. And so now what he's doing is that he is trying to prove that an electron that is a particle acts like a wave as well, just like light. All I want you to know. So this would be the one thing I'd like you to highlight. And even this equation, we're not going to work super hard on that equation, but you should still have a familiarity with it. Again, the fact that electrons, a type of particle, can act like a wave as well as a particle. And Heisenberg's uncertainty principle. So maybe he was uncertain. Sorry, that was my idea of being funny. I guess I'm not. Anyways, Heisenberg's uncertainty principle states it is impossible to determine simultaneously both the position and the velocity of a particle, meaning you cannot know where and how fast an electron is moving. So the uncertainty principle is the fact that you are uncertain on where the electron is located in a particular amount of time. There's a probability that you could probably guess or identify where an electron is located, but there's no guarantee that it is there at a particular time. Heisenberg's uncertainty principle. I would like you to know that principle. I will give you a little bit of more information in class, but for right now, that is what I want you to know. All right, so let's get into the real nitty-gritty stuff. The quantum mechanical model. So far you know, based off the Heisenberg's uncertainty theory, that we cannot correctly identify how fast and where an electron is located at a particular moment. Okay? And you should know that electrons, just like light, can act like they are a particle, but they can also act like a wave. So those are the two things we've already discussed. So now we're going to start talking about the quantum mechanical model. And what this model states is that electrons do not circle the nucleus, so not perfect orbit around the nucleus, but state the probability of finding the electron at a given point around the nucleus. So the location of the electron is often referred to as an electron cloud. So where the electron could possibly be located is somewhere in this cloud. We don't exactly know where, but somewhere within this area, we have a high chance of predicting where it could be. So kind of like these weird, it is there, but it's not there kind of thing. So the first concept I want to talk about is what's known as an orbital. And an orbital is a region of space within the cloud where there is a 90% chance of finding the electron. So pretty high chance. So electrons are more often than not found in an orbital. This is a three-dimensional region of space in which there's a high probability of finding an electron. Exactly what I stated before. A few things about the cloud that you should know is that each cloud, depending on the element, will have a different type of shape. Okay, so I know that's kind of weird to think about, but when we start talking about these quantum numbers and these orbitals, they have a different shape. Maybe you've heard of the s orbital, the p orbital, the d orbital, and the f orbital. Maybe in Science 1 you guys kind of were introduced to that, or maybe not, but it's okay. We are going to talk about it. So again, an orbital is a three-dimensional region of space in which there's a high probability of finding an electron. And this is where we're going to start talking about quantum numbers and atomic orbitals and relating the two. All right, so atomic orbitals. So there has been a lot of confusion about the concept of orbitals. And so because they have so many different sizes and shapes just based off of the different elements, because remember, each element has its own identifying features, the idea of quantum numbers has been introduced. And this is to help distinguish between various orbitals and the electrons that occupy those orbitals. So quantum numbers specify the properties of the atomic orbitals and the electrons in those orbitals. And so what I mean is that when you go to, let's say you're going to an Iowa State basketball game. When you go to an Iowa State basketball game, you obviously have a ticket. On your ticket, you have a gate number, a section number, a row number, and a seat number, meaning that no one else in that room can have all four of those exact same things. Unless somehow they stole your ticket, there's no way they could have, the same gate number, section number, row, and seat number. Okay, those are all very specific to that one seat. Yeah, maybe they're sitting right above you and they are in a different row, or maybe they're sitting in the same seat number but right across the entire arena in a different gate. So again, these are identifying features that help you identify where your ticket's at. So the four quantum numbers describe the range of possible locations for every electron in every atom. No two electrons in a given atom can have the same four quantum numbers. Okay? And the four quantum numbers are known as the principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. Remember, just these four things help identify the location of an electron within an atom. Okay, so I'm going to spend time in the next few slides describing all four of these things. We will go into detail on these in class. We will label a periodic table showing where and what these look like. So don't freak out just yet. It's going to be a little bit of information, a little overwhelming. Principal quantum number. So I think this one's pretty straightforward when it comes to if you're thinking of easiness. This one, in my brain, it makes a lot of sense. So the principal quantum number is symbolized by the letter N, and it designates the principal or main energy level occupied by the electron. Okay, so the letter N, so anytime you see a letter N, you should know that's the principal quantum number. Your values are always going to start with the number 1. So these are integers. And they begin with 1. This is the lowest energy level. So number 1 is the lowest energy level. And this is located closest to the nucleus. As the value of N increases, so N equals 2 or 3 or so on, the distance from the nucleus increases. The principal quantum number is essentially the same as the energy levels in Bohr's model. So if you remember, we have the nucleus, and then you have energy level 1, 2, 3, and 4 from Bohr's model. It's pretty well the same exact thing. More than one electron may occupy a given principal energy level, but the specific number of electrons that can be held by each energy level varies depending on the value of N. Okay, and I may shorten the word to PQN, and that's just principal quantum number. So again, these start with 1, N equals 1, N equals 2, N equals 3, N equals 4. Principal quantum number. Next type of quantum number I'd like to talk about is the angular momentum quantum number. This is represented by a letter L. That's not a 1, that's an L. It indicates the shape of the orbital. So as atoms become increasingly more what's the word? More sophisticated, I guess, if you want to say that. They take on different shapes. So orbitals of different shapes exist for most principal energy levels. And for the atoms that contain more than one electron, the different shapes result in slightly different energies for the electrons in each orbital. So the various orbital shapes split each principal energy level into one or more sublevels. So now we're getting into the idea of a sublevel, which is kind of weird. So what that means is that the principal quantum energy level, or the principal energy level, which remember is indicated by a letter N, has a different number of sublevels. So I've tried to give you an example here, but I feel like it's a little bit weird to read. So example N equals 4. So that means my principal quantum number is 4. This means I have 4 possibilities, or 4 sublevel possibilities. Okay? Because there are different shapes that these different electrons can, or these different orbitals can take on. So we're trying to say that there are 4 sublevels when there's four energy levels. Meaning you can have 4 possible momentum numbers. So you could have L equals 0, L equals 1, L equals 2, or L equals 3. Basically what I'm saying here is that the angular momentum quantum number is a number n minus 1. Okay, so if let's say your principal quantum number is 3, you have 3 possible sublevels, but they can never actually equal the number 3. So n minus 1. So I have the possibility of L equaling 0, 1, or 2. So n minus 1. I know that sounds kind of odd, but we will go over this in class, I promise, and we'll do some activities that help relate this, because it's probably like, what is going on here? And another thing you should note is that orbitals of each sublevel are designated by a particular letter. So remember, there are a number of possible sublevels based off the principal quantum number, and each one of those each sublevel has their own shape. S, P, D, and F. So S is more like a spherical shape in comparison to a P that's like a dumbbell shape. But each one of these hold their own complex shape, and as you progress, F is the most complex. The shapes and the orientation of those shapes really varies. So I just mentioned in the slide before this, when we were talking about angular momentum quantum numbers, that each possible sublevel has its own shape. And so with those shapes comes the idea that those shapes will hold or have a different orientation or a different way of looking around the nucleus. So these are symbolized by the letter M sub L. I know it continues to get confusing, and I will make sure to explain this because it makes sense in my head, but when I say it out loud, I just sound like an idiot. All right, anyway. And M sub L, and these indicate the orientation of the orbital around the nucleus. So what the shape looks like around the nucleus. Since each orbital has a specific shape, those shapes could be found in different orientations around the nucleus. So for example, if the p orbital looks like a dumbbell, that dumbbell shape could look up and down, or it could look side to side, or it could look like a diagonal region. There are 3 possible ways that dumbbell shape could be found. Okay? And I do have a table at the end of this PowerPoint, so hopefully that'll help bring things together. If it doesn't, it's okay. We are going to spend time talking about it again in class. And then the final quantum number that we are talking about is known as the spin quantum number. The spin quantum number, symbolized by the letter M sub L, indicates the direction of the electron spin. So an electron can only spin in one of 2 ways, either a positive 1/2 or a negative 1/2. Okay, so each orbital, regardless of its shape and orientation, could hold a maximum of 2 electrons, and any 2 electrons that occupy the same orbital must have opposite spins. So that's where the positive and negatives come in. And finally, we have a little table that I've put together to hopefully make things seem a little bit tied together. So the electron arrangement with energy levels. So the principal quantum number with the symbol N, 1, 2, 3, and 4. Straightforward. Lowest energy level is 1, highest energy level here is 4. The allowable sublevels. Okay, so allowable sublevels. And the L cut off there. Our S for principal quantum number 2, S and P are allowed. Principal quantum number 3, SPD, and principal quantum number 4, SPD and F. These are the sublevels that are found within these particular types of atoms. The orbitals per sublevel, so meaning per sublevel, how many orbitals do I have in that sublevel? So for sublevel S, I have 1. For sublevel SP, I have 1, 3. Sublevel SPD, 1, 3, 5, and then 1, 3, 5, 7. Orbitals per energy level, per energy level, not sublevel, excuse me, is 1, 4, 9, and 16. Electrons per sublevel, how many I find per sublevel is 2, 2, 6, 2, 6, 10, 2, 6, 10, 14. I know I'm saying this really fast, but I'm trying to make sure your video doesn't go over 15 minutes. And then finally, electrons per principal energy level are 2, 8, 18, and 32. Big things I want you to take from this, and I will star this, would be this one, this guy, and this guy. Those are the big things I'd like you to take. So associate the different sublevels with those principal quantum numbers, and then the orbitals per sublevel. And remember, these are all just having to do with the specific location of an electron. So kind of a weird way to do it, but you know, there's people out there that are a lot smarter than me. If you have any questions, please refer to Edpuzzle. Ask me on there. We will go through this, I promise. Have a good day.